And this involves the spreadsheet a lot more than you want to be involved. Next module involves the spreadsheet even more in the topics that I'm going to teach. So start getting used to that spreadsheet. That's why I have that stock project started at the beginning, to start getting you used to it. So this first thing is, in the book it's under 5.1, basic probability. We're not going to get into the horrible probability that includes counting and a lot of really hard calculations. We're going to keep it kind of simplistic because we're only going to use this idea to carry over into the next chapter, which is statistics. And the funny thing is that probability and statistics, even though I'm going to just cover it in very mathematical terms, out of all the topics I ever teach, I've always had students come back and say, thank you for this one topic, because they use it on their job. Collecting things and looking at things and figuring out what numbers mean. So probability is based on a couple things. Outcomes and events. Now, an event is an outcome, so it's part of the outcome. That is the first thing we have to talk about. But outcomes on their own is anything, and I'll put it in a study, looking at, experimenting with, but I'll just use the word study. So if we're looking at traffic patterns, and we're watching the stoplight out here, and we're watching as cars go through the light along Tarboro Street, we're going to count all the cars that go through the light, whether they go through a green light, the yellow light, or my favorite one, the red light. So those would be the outcomes. Now, out of all of those events, we might be interested in only one of them, the ones that actually go through the red light. So an event is an outcome we are looking for. The outcome that we're looking for. So probability based on this events and outcomes is literally the probability of an event. I want you to get used to this notation. P parentheses E reads literally the probability that the event E will happen. That little P parentheses E means that entire sentence. And one thing, of course, you have to know about mathematicians is they're very lazy and they hate writing things down. So they'd rather replace it with a symbol rather than a bunch of words. So you see this, and this is just the probability that event E is actually going to happen. And it's defined to be the number of events
times out.
Don't you dare. Look at that, I put EE, and that's fine. EE events. Divided by the number of outcomes. It is a ratio. Kind of like what we were dealing with last chapter. And a lot of the things that we did in the last module are going to carry over here because we're still going to be dealing with percents and fractions and ratios and all that fun stuff.
It's supposed to be 2 E's.
No, I don't know why I put 2 E's. So, number of events out of number of outcomes. Okay. Let's do a simplistic type. For example, let's put it as high school graduates. You know, kind of like a Reunion. Of course, there's men and women. And let's say they have 2-year degrees or 4-year degrees, split up. And let's give them some numbers, 21, 38, 15, 25. I wonder if it's true that more women go to their high school reunion than men.
Yes,
Is it?
yes.
Yeah, because I never went to mine. Okay, so what I'm interested in is 1. What is the probability of randomly, eventually I drop the word randomly and you start getting used to the idea that when you do probability, you randomize everything. You close your eyes and you reach in a bag and grab something. So what is the probability of randomly selecting a man with a 4-year degree? You know, put their names in a hat, shake it around, and pick a name out. So when you see this problem, it actually kind of goes back to how we were doing things in the first module. What do you think we should do to this table first? Add them all up. So this becomes 59. This one becomes 40. If we go this way on the men, it's
36 and 63.
3 and 36. For a grand total of?
99.
I should have made it 100. Oh well. 99. All right, so when I say what is the probability of random selecting a man with a 4-year degree, what number do you look at?
15.
The 15. So when we say what's the number of events that could happen?
It's 1999.
Number of events. The event I'm curious about is a man with a 4-year
36.
degree.
Would have been 36.
I just circled it.
15.
I know, but then I start hearing all these other numbers, and I'm like, I circled it. This 15 represents men that happen to have a 4-year degree. So when I say, what is the probability of selecting a man with 4-year, you know, the probability of selecting a man with a 4-year degree. Yeah, my blue marker. Do it in green then. Ooh, better color. The probability of a man with a 4-year degree is equal to the number of events divided by the number of outcomes. How many events are we talking about? 15. How many outcomes? In other words, as I randomly select that name out of the hat, how many were in there to begin with?
36.
99. Why would I
total.
exclude the poor women? Don't be prejudiced. Sexist. So the probability of selecting a man with a 4-year degree out of the whole room is 15 out of 99. So another way of reading this is 15 out of 99. I gotta get you used to that because that's how they're written in Moodle. If you're gonna write it in fraction form, you're gonna be looking for these two numbers. Be careful. If it was 15 out of 100, you have to reduce it. They both have a common factor of 5 then. But 15 out of 90, oh, no, they do have a common factor. 3. 3 goes into 15? Out of
33.
33. So you have a 5 out of 33 chance of selecting a man with a 4-year degree. Now sometimes these things are going to get a little bit more complex.
So, okay, which one you gotta put in?
The way that it's in, some of them are written in Moodle, if the fractions are rather small, it'll have out of as the language. So there'll be a box here for the 5 and a box for the 13.
Okay.
The
And if it's
33.
not,
And if there's not, then it'll be usually percent. Or there's a possibility you can actually write things like this into your cell and it'll mark it right. But it'll say you can write it as a fraction.
So what if we put 18 out of 99? Would it be wrong?
It'll mark it wrong, yeah.
reduce
You have to reduce it. It's looking for the 5 and the 33.
it.
It's gonna ask you to reduce it to the one.
I shouldn't even have to ask you.
Okay.
If it's a fraction, you always should reduce it. I love when people leave 2/4 on the test. 2/4. This, by the way, I haven't cleared it yet. This is called empirical probability. When you have physical numbers involved, we call it empirical probability. All right, while we're on that table, let's do all of them. On the screen, it'll go off, but 2.
It's really the same question. I mean, the same box.
Same box as that one, the men and the women, the 2-year and the 4-year degree. What is the probability of randomly selecting a woman with 4-year? So the probability of this event will equal
25 over 99.
25, the women that have 4-year degrees out of the total number of 99. So that'd be 25 out of 99. Does that one reduce? No. All right, 3. What is probability of selecting a man with 2-year?
21 out of 90.
21 out of 99. The 4th one I'm not going to write down. A woman, or all the way, with a 2-year degree. 38 out of 99. Now this is one of the only cases where I'm going to do the following thing.
One moment.
Each one of these fractions.
One moment, please.
No problem. Pause. Yes.
Why we couldn't use, 59?
59 is just the sum of the 2-year degrees. I'm not asking what's the probability of selecting a man who already has a 2-year degree. I'm saying what's the probability of selecting a man who has a 2-year degree. It's a little, one of them is a conditional probability. We're not going to talk about those just yet. The other one is just a straight up, I'm looking at this number out of the total thing. What you're thinking of is what's called a conditional probability. Out of the 2-year degree people, what's the probability of selecting a man? That would be 21 out of 59. But I have to separate the 2-year away from everybody else. As long as I don't do the separation, don't worry about it too much.
So when we use the 59, like, that's like a probability of being equal, 59, like, you know what I'm saying?
Are we gonna ever use?
Yeah.
Oh, the conditional? Yes.
Okay.
Several times. A lot. And you're going to hate it. Because the language gets really strange about conditional probabilities.
No, we always have to do.
Please do. Did I forget to reduce someplace? Really? What does it reduce to?
7.
7 out of 33. There's a reason I don't want to reduce just yet. I'm trying to show one more thing. If I change these all to percents, just for the fun of it, what is 5 divided by, how do you change 5 out of 33 into a percent?
5 divided by 33 times 100.
And change, put a percent sign, right? So what is 5 out of 33
0 point.
I got
as a percent?
15.2.
15.2% of the time you will select a man that has a 4-year degree. All right. What about 25 out of 99?
25.3.
What's that as a percent?
25.3.
25.3%. All right. What about our 7 out of 33?
21.2.
21.2.
21.2% of the time. So you can always change probabilities into percents or decimal values. Either one works perfectly fine. But most people lean towards the fraction, the out of, or the percent, and try to stay away from the decimal value. And the last one is 38 out of 39? 99? which is equal to
38.4.
38.4%. Now, only one thing is going to mess us up is probably the rounding, but let's see what happens. This is the one case where you can take percents and actually add them together. Remember, last module I said, don't you dare ever add percents together unless you know more about it. Well, the thing that's nice about each one of these is they all started out over 99. Each and every one of them, out of 99, out of 99, out of 99. And as long as your denominator is exactly the same for each one of your ratios, then your percents, you can just add them up. If you just have a bunch of percents in front of you, though, don't you ever dare do that unless you know the denominator is exactly the same. So let's take these and add them all up. 15.2, that one, that one, that one. And what do they add up to?
100.1.
Yeah, the rounding is going to throw it off.
100%.
It should add up to 100%. But because of rounding, we get that 0.1 in there. Now, if you just added the fractions, 1599s, 2599s, 2199s, 3899s, you'd end up with 9999s, better known as 100%.
Isn't it round on the
So, the sum of all probabilities based on the same group equals 100%. That's one thing you have to realize. That if you add up all the possible probabilities of an outcome, all the cuts of an outcome, as long as they don't overlap, men are men, women are women,
It's always
2-year
gonna
degree
come
is
to
separate than 4-year degree. All the events always have to add up to 100%. Kind of like, what's the probability of being a man?
50%.
No, not in this chart.
Ah.
There are 36 out of
99.
99. What's the probability of being a woman? 63 out of 99. And if I say what's the probability of them added together, it should add up to 100%.
Oh.
Okay.
And the same thing, if I separate it 2-year to 4-year, you should be able to add them together and get 100%. So, that's really important, that the sum of all the probabilities of an outcome, all the possible outcomes, is 100%. Now that's empirical.
So we have to add all that together.
I'm using it as an example to emphasize that if I have this outcome and I cut it up into a bunch of pieces, and I say the probability of each one of the pieces, if I add all those pieces together, it always has to add up to 100%, because you're dealing with all the outcomes out of all the outcomes.
So that's like a way to check your work, because you know if it doesn't equal 100%, but
It's a way of actually finding a shortcut to find some probabilities for another reason. Let's do theoretical for a second. Theoretical
This is gonna be a move.
probability. Oh yeah.
I'm talking about that theoretical probability.
Yeah. Everything I put on this board, anything I teach you, you have to work with, do. Now, where empirical probability is, you generate experiments. You go to the stoplight and you count the cars going through, and the numbers are coming from observations rather than what we're going to do here. Theoretical probability. Flip a coin. Flipping a coin is very theoretical. Why?
Flipping a coin is theoretical because
This is not always gonna end up on the same.
Yeah, but it only has two sides. Heads,
It's
tails, right? And the assumption is half the time it's going to land on heads, and the other half of the time it's going to land on tails, unless you have a coin. I had one once that had two heads on it. Someone ground out the tail and cut up another coin and threw the head inside of it, and I would flip it and go heads, heads, you know. But flipping a coin, half the time
50%.
you get a head, and half the time you get a tail. Do you believe that?
Yes.
But what does it mean? That's a little different. Does anybody have a coin that I can flip?
I do.
Quarter. Don't dare give me a penny. Those are almost impossible to flip. Throw it up here. Throw it.
I don't want to hit you.
Throw it. Throw it. High arcing.
Ah.
Ooh, I almost had that. She's trying to take away my possible children. All right. Ready?
Heads.
Oh, and it does have heads and tails. It's not a chibi coin. The other assumption is, do you ever hear of a weighted coin? When you flip it, it'll naturally want to land on the heavier side. There is a slight difference between a head and a tail on every coin, but hopefully it doesn't pop out. So, theoretically, half and half. What I'm going to do now is called what?
Flipping.
Yeah, but what kind of probability will it create?
Theoretical.
It's not theoretical because I'm actually going to.
It's
It's empirical. I start flipping this and start counting how many heads and how many tails. It becomes empirical. So someone take a record. My first toss is a head. So I have a little column HT, do little tick marks. The first toss is a head. Second toss is a tail. Wow, that sounds like 50-50. Where'd you go?
More 50-50 than that.
Can't get more 50-50 than that. One head, one tail. A little chart. Head, tail. So far I got 1 to 1. Alright, next toss. Maybe this is a really fair coin. Head. Head. Uh-oh. Tail. Wow, it balances out again. Tail. Head. I'm trying to change how tail. It's not doing what I expected.
We just say heads and tail. We don't take your word.
Nope. Tail.
He said no.
Experiments are different than tail than anything else. Drop it.
So, Mr.
Head.
K, if you was using
Head.
something like you was throwing dice and it's
That's something else. Hold
more
on.
than-
Tail.
right.
Wait a minute.
Head. Head.
I am.
Tail. Why, you're not? Head. You waiting for me to mess up? Head.
Yeah, you don't drop it 2 times.
Ah. Tail. Woo. Head. Tail. Ooh, that was a good flip. Head. 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 I know, really. Tail. How many is that? Total flips.
11 tails and 10, 14 heads.
11 tails, 14 heads. That's good enough.
I have 25.
11 heads.
Yeah.
No, you got more than
I
that.
just wrote mine out. I didn't do like.
5, 10, 15, it was 16 heads.
Oh.
16 heads, and 5, 10, 13 tails.
Got 14 heads and 11 for tails.
Wow, you all pay attention really well if the numbers are all different like this.
No,
But,
it was 14 and
Either one.
11
Three
because
people
I was
got the
ticking.
same number.
what, 1, 14 and 11?
Yes.
Alright. So either if it's 16, 13, 14, 11, it's an increase of 2 on both of them. It really doesn't really change much. But even if we did 14, 11, is it half and half?
No.
No.
Wait.
The probability of heads is 14 out of
25.
25. The probability of tails is,
11 out of 25.
and if I add them together, you get 100%.
Yeah, she gonna say.
What did it 16, 13?
Oh, someone came up with it.
Oh,
Oh.
I was seeing
Oh.
11 and 14.
I don't want to steal your quarter. You might charge me interest. So, where theoretically it should end up half tail, half head, in real life you only get 14 out of 25, 11 out of 25, close to half-half. What's 14 divided by 25 as a decimal?
What's it?
0.56.
0.56? 6. Better known as 56%.
Yeah.
And 11 out of 25?
44%.
And they add up to 100%, the way they should. So they're relatively close to 50%. One's a little shy, one's a little above, and they're off a bit. Here's the cool thing. If I kept flipping head, tail, for thousands of times, 100,000s of times, eventually what happens to those two fractions is they become really close to 50%. One might be 51 and the other one might be 49. And eventually you'll get to 50-50. But that's what's called the law of large numbers. You have to do the experiment so many times to actually end up with the theoretical probabilities. So there are cases where we just want to work in theoretical land. They're perfectly half and half. There's other cases where we want to actually do the experiment and see what kind of probabilities are generated. It depends on the situation. If you can do the experiment, it's usually better. If you have to deal on theoretical, deal with the theoretical.
What does 25 come from?
14 plus 11.
Okay.
Number of
So
outcomes.
that's the total.
Yeah, when you total these two up,
Let me write total.
this 25, this
Okay.
becomes the outcomes. The total number of outcomes. Remember, probability is number of events that you're looking for out of total number of outcomes. Total number of outcomes. All right, so that's just one coin. Who flips just a single coin? No, not mathematicians. Single coin is boring.
Oh, you gonna draw up 3?
Let's flip 2 coins.
Who give you the life?
So you don't need a quarter.
Nope, I'm not going to sit here and flip 2 coins. We're going to do this one theoretical rather than empirical. Now, when we flip 2 coins, the assumption is you do one in your right hand, you do one in your left hand, and you read it left to right. So a head-head would be your left hand head ahead, your right hand head ahead. Or you color them a blue coin and a red coin, so you can distinguish them. So when we're dealing with 2 coins, we could flip both of them and they would be a head and a head. What's the other possibilities?
Tail, tail.
Tail, tail. I'll put that down here.
Head, tail.
Head, tail. I'll put that here.
Tail, head.
Tail, head. So order is important with this type of probability. What happens to the first one and what happens to the second one? Now, technically, head, tail, and tail, head seem the same, but they're a little bit different. This one would be your left hand head ahead, your right hand head a tail, and vice versa. So what is the probability of head-head? If, oh, by the way, this is called the outcomes. Those are all the outcomes of flipping 2 coins.
1 and 4, 1, 4.
1/4, right? There's
25%.
one head-head there out of a total number of 4. So it's 1 out of 4. All right. What's the probability of the same?
2, 4, 1/2.
2 out of 4. Head, head, tail, tail. Better known as
1/2.
half the time. So it has the same probability of just flipping a single coin.
So the same as head, head, tail, tail.
Head, head, tail, tail.
I wrote it right now.
What if they're different?
Same. 2 over 4.
Head, tail, and
Tail, head.
tail, head. That's 2 out of 4, better known as a head. So as long as you have all the outcomes sitting in front of you, finding the probability is simple. You count how many there are, that'll be your bottom number, and you look for the ones that you're looking for, the events, and you put that as your top number. Okay. Sounds reasonable. 3 coins.
Oh,
Late.
you don't want 3 coins.
Oh, by the way, coins and children are the same. Coins and children are technically the same because
The 3 keys and 3 forms different.
wait a minute, you have a male, a female, and that'd be really scary. An alien. So coins and kids are about the same. What's the probability of having a male?
50%.
49.8%. Probability of getting a female? 50 point something percent. It's a little bit higher on the females now than it is on the males. And what's funny is they've been studying the effects of pollution on populations, and as things get more toxic, I think more females are born than males, so that you have a more chance of spreading your gene pool. And then if the environment gets cleaner, you get more males than females.
If you look over time, it always,
It fluctuates.
always been like that.
It's everything cycles.
Evolution has always been like
Everything cycles. It's really
We
cool.
used to can have more than one wife that in balance.
Well, so heads you can think of as boys, tails you can think of as girls. So your probability of having 2 boys in a row is 1 out of 4. Your probability of having 2 girls in a row is 1 out of 4.
Well, my mama had a girl, boy,
Girl, boy, you're the in the middle there. Now, if you have 3 coins, that would be like having 3 children. So what's the first possibility with 3 coins? Flipping all
Head,
head.
tail.
And tail, I'll put over here.
Yeah.
Those are what I call the
Head.
main groups. Here's how you come up with the subgroups, the underneath.
Hold on.
So here's the trick. You start off with head,
Mhm.
and you change the last one to a
To
tail.
tail.
So you go head, tail. Then you take that tail and you move it one to the left, one to the left. So it becomes head, and tail, head. Okay. Over here you do the same thing. It's tail, head, and then you move the head to the middle, and then to the front. This is all the possible outcomes. How many are there?
8.
8. So if you're flipping 3 coins, you have 8 different possible outcomes. So if you think of HHH as boy, the probability of having 3 boys in a row in a family is 1 out of 8. So the probability of 3 H's, there is exactly 1 of them out of a total of 8.
So the whole time that last H, you just move it across the whole time?
Yeah. You take the HHH, you throw a T at the end, and then you move the T to the middle and T to the front.
Oh.
It gives you all the possibilities.
Oh, okay.
Head, tail, head, head. All right, what's the probability of 2 heads?
Wait,
1, 2,
Two.
2 out of 8.
3 out of 8.
3 out of 8.
1,
Oh,
2,
yeah,
3.
1,
Show it.
This one
Yeah,
has
3
2
out of
heads.
8, yeah.
This one has 2 heads. This one has 2
Yeah,
heads.
3 out of 8.
So this would be 3 out of 8.
Smart.
So when you have all the outcomes listed, all you have to do is look for the ones you're looking for, count them up, that goes to the top number. All of them become your bottom number. All right, so that's 2 coins.
3.
No, well, 3 coins. Now let's do a die. What's a die?
A dice.
The dice.
Two.
A single
Oh,
dice.
1,
It's singular for dice. Dice is actually plural. So a die, what does a die have on it?
6.
6
It has 6 sides, just like a cube.
Goodness.
And they, of course, have little dots on them. I don't know the order of them. And the biggest dot is 6, and the smallest one is 1. So basically, it just counts up all the sides of a die. Now, if it's an unweighted die, we're not talking about the cheaters with dice, we're talking about an official die, then you have only this as your outcomes.
1 through 6.
It's going to land on a 1, a 2, a 3, a 4, a 5, or a 6. It has to land on one of those sides facing up.
Anybody got dice?
Alright. What, we going to gamble? I'm going to teach you why gambling is pointless, eventually.
Really?
So, what is the probability of rolling a 1?
1 over 6.
1 out of 6. What's the probability of rolling something bigger than a 3?
3 out of
3 out of
6.
6.
What's bigger than a 3?
4, 5, 6.
4, 5, 6. 3 out of 6, you better write that as
50. 1 over 2.
1/2 or 50%. Okay. Probability
I wrote even numbers.
at most 3.
Huh? What?
Three
I
out
love
of 6.
words.
Probably
At most 3. What does that mean?
3
Zero.
out of 6.
3
out of
at
6.
least 3.
When you
3
say-
or more.
1, 2, or 3.
If I wanted it to be 3 or more, I would have said at
Oh.
least 3.
That's
Because at least 3 is,
At
the
most.
3 is the
Oh, that
small.
means 3 or less.
3 or less.
Oh, okay.
So it's 3 or less, so that would be 3, 2, and 1, which is
3 over
1/2.
6.
3 out of 6. Better known as
Yeah.
a half.
Sounds good.
What was this?
He graded at this.
Is that greater than 3?
0.
Which one was here? At most 3?
You can do 1.
1 out
Oh
of
yeah, that's
6.
greater than 3.
Bro, wait. Four.
Zero.
On the road, it's
5.
At least 1.
More than
All
1.
over
Just
5.
1.
Oh,
6 out of
5 out of
6.
6.
Oh, that's
It's 6 out of 6.
It's 6 out of 6.
Yeah, that's 6 out of 6.
Because at least one means it's 1 or
Or
2,
more than
3,
one.
4, 5, or 6. So this is
Okay.
6 out of 6.
I'm
Better
gonna
know
test my
that.
idea so I can win some money. They ain't gonna be one. That's 6.
Careful.
You
Zero.
have a 0 out of 6.
0 out of 6, better known as
Zero.
0. So these last two probabilities are important. Kind of like the sum of all your probabilities has to be 1. Has to be 1. This is another thing about probabilities. The probability of an event has to be between 1 and 0. That's a fancy notation for between 1 and 0.
That's why I wouldn't miss a bit.
Now, some books will put equals here, but there's a word for 0. What's the probability of 0 mean? Probability of rolling a 7. What does it mean?
You get 0.
Are you ever going to get it?
No.
No. So this is called
Impossible.
impossible. So on this end of it, it's
Unless you have 2 dice.
So it's like impossible.
possible.
2 dice you can roll.
And 1
It's possible.
is not just possible.
Extremely possible.
It's not even just extremely possible.
It's all possible.
It's going to
Happen.
happen. This is certain.
Oh, sir.
So all probabilities are somewhere between impossible and certain. There's only certain things that are certain in life. What are they? Death and
Taxes.
taxes.
Wait, what?
And if you remember the words that go with impossible, usually you say,
Yes.
generally the word in front of impossible is,
He gonna die.
nothing is
Right.
impossible. So if you think something is impossible, you'd have to put an equals here. If you think something is absolutely certain, you put an equals here. Let me give you this as an example. It's a bad example, but let's go with it.
We will need it.
What is the probability the sun will rise tomorrow, assuming there's no clouds?
100%.
You would think certain, right?
100%.
But is the sun going to be around forever?
No.
No. But more than likely, it's not going to disappear
Tomorrow.
tomorrow.
How you know?
More than likely. They've done studies that the sun is in its middle age. You know, it's like 40, 50 years old in human terms. So it has a few more years to go.
I was looking at you.
They know the stages of the sun and what it looks like when it's about to die. You know,
So a few more years is what, 2, 3? 'Cause a few
Billion.
is 2.
a billion.
Oh, good.
We get back into those really big
I was
numbers.
get live like that.
How long's the sun been there? According to the Bible, about 5,000 years. How long's the sun been there?
Some of
5,000 years BC.
No, how old was the sun? No one knows how old the sun is. Don't you read any science books at all?
I mean,
They used to have it at a billion. Then it went up to
a trillion.
4 billion. It's not a trillion. The biggest number I've seen lately is about 7 billion years old.
The sun.
The sun. It's been around for 7 billion and it'll be around for another 3 or 4. So are we going to worry about the sun?
No.
Alright,
So the 0 is impossible.
now the other thing is nothing's impossible. I was flipping a coin one time, having fun with it, and letting it land on this. Are you done? And I was flipping it on this table, letting it land and hop around. Now remember, 50-50 chance of head and tails. It was an older coin, so it had a very flat side. It actually landed
Both and
on its side and stood up. So it was neither a head nor a tail. So that nothing is impossible kind of
Went out the window.
comes in. Because when you talk about probability, you're talking about lots and lots of different possibilities. We try to keep it narrow-minded, so don't get crazy. So probabilities are always between 0 and 1. So if you get a calculation, you do some calculation, and you do a probability, and it ends up being negative, guess what? You did it wrong. It can never be negative. If you get an answer that is larger than 1, like 4 out of 3, you know you did it wrong because it can't be bigger than 1. So that's really important. Nothing smaller than 0, nothing bigger than 1, absolutely. Coins. If you had 1 coin, you had 2 choices, head, tail. If you had 2 coins, you had 4 choices, head, tail, head. tail, and tail.
Yeah.
When we went up to 3 coins, it was 8 choices.
Wait.
Yes.
You don't believe me?
Oh, I know where you're going with this. You
Okay.
can do 2.
Well, how many choices on the first one times how many choices on the second one? So with coins, if we had 3, it was 2 times 2 times 2. So here's a cool one. If you have 5 kids, what's the probability of having all girls? Well, it's 2 for the first one, 2 for the second one, 2 for the third one, 2 for the fourth one, and 2 for the fifth one. So 2 times 2 times 2 times 2 times 2. Better known as?
2 to the 5th power.
Better known as 32.
Oh.
So, if you have all girls in a family of 5, that's a 1 out of 32 chance. My wife comes from a
Are
family
you
of 5
gonna do a
girls.
problem on the board with the children?
Children and coins are exactly the same.
I'm asking you, can you do a problem like you're talking about? Because you're gonna give us a problem about the children
Not that many.
on the test.
Maximum 3. And children and coins are the same. So, there are 6 possibilities on the first dice. There are 6 possibilities on the second dice. So, this is the total number of outcomes.
So it's 6 times
36 is funny.
No, that ain't what's funny. But
Great. Shh.
Somebody said it.
Now 3 dice, of course, gets a little messier, 6 times 6 times 6, but we're never going to get there. So here's the thing we're going to do with dice. If you roll this up here, what did you roll?
6.
A 6. Virginia, door's right there.
Oh.
Total number of outcomes.
Please.
Hmm.
Thank you.
What?
Shh. So, if this is a 6, how many different ways can you roll a sum of a 6?
1 plus 5.
Okay, and that's the best way to do it. 1 and 5,
2 and 4.
2 and 4,
Like on the board, 3 and 3.
3 and 3.
That's it.
Now be careful. Left hand, right hand, left hand, right hand.
5 and 1.
5 and 1,
4 and 2.
4 and 2.
4
3
and
and
2.
3 is exactly the same.
The 3 and 3.
3 and 3 is exactly the same whether you have it left hand, right hand, right hand, left
Is we
hand.
still doing the dice one?
We're doing 2 dice. So if I rolled a 2 and a 4, that adds up to 6. But the other ways of rolling a 6 is a 1 and a 5, a 2 and a 4, a 3 and a 3, or a 5 and a 1, and a 4 and a 2.
Oh.
Flipping a 3 and a 3 doesn't really change what you roll. So if I said, what's the probability that your sum is a 6, how many of them add up to 6?
5.
5. Out of
6.
36.
36. Yes.
total number of outcomes is 36. So what's the probability that the sum is 7?
6 and 1, 1 and 6.
So 6 and 1, 1 and 6.
5 and 2.
Oh, I get what you
5 and 2, 2 and 5.
3 and
3
4.
and 4.
3 and 4.
4 and 3.
0. There is no 0 on a die. There is no 7 on a die. Remember we talked about that earlier? So the probability of the sum of a 7 is those out of 36. So this would be
7,
6 out of 36, better known as?
1, 6.
So it is more likely to roll a 7 than it is to roll a 6. What's the most unlikely rolls?
No even numbers.
Even numbers? Those are probably more than likely.
12.
Um,
Some
12 is one of the hard ones. What's the probability that the sum is 12?
1,
1 out of
36.
36. What's the other hard one?
Snake eyes.
Snake eyes.
I mean 2.
2.
Row 2.
1 out of 36.
Those are the two hardest rolls to have. Snake eyes and boxcars. Boxcars.
Sound like somebody been gambling.
My other math book has got the
So-
whole rollout of doing the dice.
So, yeah, it does, but I'd rather you do it. Come
I'm
up with
talking about
sums.
this math book.
I know.
What's a box score?
What?
What's a box score?
2 6s.
Oh.
Boxcars.
I didn't know that.
Really?
He
Oh.
know.
Yeah, everybody knows snake eyes, 1 and 1, but 6 and 6 is box cards.
I know that.
Oh, I didn't know them.
What, how you, what do you get a box for?
Box cards, because they look like box cards. You know how the 6s are arranged? Makes it look like a box card. Trained, I guess. I don't know. I've always known it as box cards. Alright. So coming up with sums is a probability thing that you should be able to do. There are questions on this, so make sure you know how to come up with the list. Don't forget to reverse them, but if they're exactly the same, you can't reverse them because reversing them is useless because it's exactly the same.
Okay,
Well,
for the sum
a
of
sum of
six.
5.
Sum of 5?
2, 3, 4, 5.
Huh?
What would be the probability of a sum of 3, or a sum of 4, or sum of 5?
Sum of 3 would be 2, 1, 1, 2.
So 4 out of 36.
2 out of 36. Sum of 4 would be 1, 3, 3, 1, 2, 2. 3 out of 36.
Okay, so that 1, 6, 5, 2, 5, and 4, 3 go for the sum of 7, right?
So,
Yeah, but the
These here are 7.
yeah,
These here are
6.
5.
Okay, because I'm just,
Six.
okay,
And that's
okay,
seven.
because this is confusing me.
And these 2 down here are just the rarest ones.
You got it.
Oh, I do that all the time. Alright.
No, I don't understand box cards.
Next thing I'll ask you about probability-wise. Cards.
Oh,
It's
52.
I don't get too tricky with it. I try to keep it simple. And my question gives you the breakdown of what's what in cards. The first thing to know is how many cards are in a deck.
Are you counting the
52.
jokers?
No jacks, no jokers, no garbage.
Jokers makes it 54.
52 cards. They are split up into 4 suits.
Yes.
Hearts, diamonds, clubs, and spades. Always the most interesting one to draw. So, and 2 of them are red and 2 of them are black. These 2 are red. These 2 are black. So, if there are 52 cards in a deck, how many of them are red?
26.
26. So there are 26 red cards and there are 26 black cards. How many of them are hearts?
13.
13. There are 13 hearts, 13 diamonds, 13 clubs, 13 spades. Take a guess what 52 divided by 4 is.
13.
13. Okay. There are things called face cards.
Yeah.
Face cards are the ones that actually look at you. Which cards look at you?
The jacks, the kings, and the queens.
The jacks,
The queens and the kings.
jacks, queens, and kings.
And it's only 2 jacks on it.
There are 4 jacks, 4 queens, and 4 kings because you have hearts, diamonds, clubs, spades of each suit. We're gonna gamble with you, dollar ante. We'll make a profit. So, if you're not a jack, a queen, and a king, you're either a number card,
Or ace.
2 through 10,
Yeah.
or you're an ace.
Yeah.
So there are 2 through 10 number cards of each suit: hearts, clubs, diamonds, spades. And then there is the ace,
4 ace.
which literally has an A on the card. So using this information, you should be able to come up with lots of probabilities based on a deck of cards. So the assumption is this: you always shuffle. What that causes is randomization of your cards, and you have to shuffle them really well. If you ever opened up a brand new deck of cards, if you started playing with them right away, things would be really messed up.
Yeah.
Because they come in order.
Yeah. Let's see.
So you shuffle them really well, and then we're just going to randomly select. Think of it as a magician. He's going to fan out all the cards and say, select any card. And you can randomly choose any card in there. So what is the probability of selecting a king randomly
Disregard the
out of a deck of cards?
Disregard.
4 out of 52.
There's 4 kings in a deck of cards, so that would be your number of events. And there is a total of
52.
52 cards. Oh, I've got to ask this silly question. It has nothing to do with cards, but people's brains are funny. How many states are in the United States of America?
52.
50.
50.
It's 48.
It's 50.
Wait, oh,
50.
oh, 50.
50.
Two
What was
of
the
them.
50th state?
Hawaii.
Hawaii. There is not 52. There's, a couple
We're talking about cards.
territories.
I got.
But it's 50. There are 52 cards in a deck of cards. There are only 50 states. Okay. What's the probability of selecting?
Why would
Uh,
you do that?
Because I find it funny that a lot of people think there's 52 states because there's 52 cards. They get that it's in their brains, or they think the Dominican Republic and Guam are states, but they're not.
Okay.
A lot of people say 52 though, or 48, which I think is even funnier. Where are you from? The 40s? So, what is the probability of selecting just a number card? Now you have to figure out how many number cards are there. So you start with one of the suits, hearts. There's the
40.
2, the 3, the 4, the 5, the 6, the
It's
7,
40.
the 8, the 9, and the 10. So there's only 9 in each suit.
4 is 36.
So you do 9 times 4 for the top number out of
6, 52.
52. So this is
So
36.
10 not a number card?
Well, you account for
The
10.
first number card is 2.
Oh yeah, I forgot it's not a one.
Ace is just
yeah.
ace.
Oh yeah,
Ace
you're
is
right.
just
It's
ace.
number 36.
So does 36 out of, oh, I'm sorry, does 4 out of 52 reduce? 1 out of 13. 36 out of 52 reduce?
1/2. No.
Oh, no.
Definitely not 1/2.
9
Look
over
at
13.
26.
9 over 13.
9 out of 13.
Go.
So the probability of selecting a number card, just a number card, is 9 out of 13 cards. 9 out of 13 tries. When would you care about picking a king and a number card? Has anybody ever gone gambling?
What have you what?
Blackjack?
Oh,
Blackjack
Vegas.
is, and you have those people trying to count cards.
Yeah.
Of course, that's messed up because they don't use one deck.
Can you teach us how to count cards?
They use about 7. They'll shuffle 7 decks together to do any of those games so people cannot count and know how many cards.
It's, you can still do it.
You can do it, but boy, you have to be really.
You gotta be really good at counting cards.
Can you teach us how to count cards?
Nope,
You can stand.
I wouldn't even want to try it myself.
Chicken winner, chicken dinner.
Chicken.
Yeah, what was that one?
Rounders.
What is the probability of selecting a
Wait,
black
wait, wait.
face card?
3.
Oh,
10.
2
I
out of
mean, no,
52.
20. No,
2 out of
18.
52.
18.
Start with face cards. How many face cards are there?
26.
It's 18.
Oh.
4, 3.
Six.
Wait, black for a face card.
Well,
How many?
Six.
You're all. You're throwing numbers up there. How many face cards are there?
well,
12.
Why? Because there are 3 face cards per suit, and there are 4 suits. That's a total of 12.
Oh,
How many of them are black? I think I ripped cards apart. Do you want to try one more?
So the ace is not included.
The ace is an ace. And
that's
it's its
separate.
own little group, just like the king is a king, the 5 is a 5. What's the probability?
One out of 10.
That's right. No, you'll never get 1 out of 10 out of cards. What's the probability of selecting a king or a heart? Now this one you better not shout out answers. 'Cause I guarantee you it'll be wrong.
Because the king can be a heart too, right?
Because the king can be a heart.
Yeah.
Awesome. So here's our problem with this. It would be fine if I said, what's the probability of selecting a king or a red ace? That one would be easy. Because a king and an ace have nothing to do with each other. So what would this probability be? A king or a red ace? So you ask yourself, how many kings are there?
4.
4. How many red aces are there?
2.
So I take those 2 and put them
Yeah.
together. So technically this becomes the probability of a king plus the probability of a red ace. Where the probability of a king is 4 out of 52. The probability of a red ace is 2 out of 52. Most people don't do that though. But I need to show you how this is different than the king or the heart. So we have probability king, probability red ace. We can add them together. They have a common denominator. That would be 6 out of 52, which is the same as
3
my
over
face,
26.
which is 3 out of 26. This one, we're going to have to handle a little differently.
You're gonna include 5 for the
I know this is black. Let's switch color. So let me go back to this. We'll come back to this table often just to talk about breakdowns of what's going on. I'll keep the numbers kind of small now. 7, 9, 13, 20. Just making them up. So here we have a room of people. They're separated into 2-year and 4-year and male and female. So total of 2-year
20.
is 20. Total of 4-year,
29.
totaling the other way, 16 and 33, for a grand total of 49 in both directions. What is the...
Did you already add them up already?
Yeah.
Oh.
What? You said something to her, didn't you? What's the probability of selecting a 2-year degree or a male?
Wait,
He asked about
The what?
the chart. He asked what they had to do with that problem.
Oh, I'm getting to it.
What you said.
I'm getting to it. So, if I'm looking at a 2-year or a male, how many 2-year people are there?
20.
There's 20, right? So I would say 20 out of 49. So that would be the probability of 2-year by itself. What's the probability of male by itself? 16 out of 49. And you would think, just add them together, right? The problem is this. When you look at the males, they go this way, right? And you look at the 2-year, they go this way. So when you come up with the total 60 and 20, they share a common sum number. What's that sum number?
7.
That's 7 up there. That is added into both of the numbers 20 and 16. So since it's in 20 and 16, and I really only want to count it once, I need to subtract how much? 7. What it does is it takes it away from one of them and leaves it in the other. So this would be 7 out of 49. All right. So 20 plus 16 is
36.
36 minus 7.
29.
So this probability would be 29 out of 49. So what's the difference between that and looking for a king or a red ace? This one, they have something in common. A king and a red ace have nothing in common. There's fancy words for it. One's called mutually exclusive. The other one is not mutually exclusive, but I don't want to get into that language. Go ahead. Okay. So this is what's considered overlap. If they overlap, you have to take away the overlap. So, go ahead.
You subtract the 7 because.
It's overlapped.
Okay.
When you add up the 2-year degree, you go 7 plus 13 is 20. When you add up the males, it's 7 plus 9 is 16. So if I try to add the 20 and the 16, I'm actually adding that 7 twice.
Okay.
And I really only want to add it once, so I have to take away the overlap. All right, so what about that probability of a king or a heart? So I guess one of the main things here is or becomes what operation automatically? Plus. It automatically becomes plus because over here we just added 452 and 252. Just added them straight up. The subtraction only comes in if you have a little bit of overlap. So the formula is going to be the probability of a king plus the probability of a heart. But once you write that down, you know there's an overlap. There's something called the king of hearts. So you're going to take away the probability of king. What word would go in between, I wonder? And. Heart. I want to get rid of the king of hearts because it's a king and it's a heart, and I don't want to count it in both locations. So what's the probability of the king?
4 52.
4 out of 52. What's the probability of a heart?
13 out of 52.
13 out of 52. Don't reduce these fractions because you'll have a common denominator all the way across them. Minus, how many
One.
kings are hearts?
1.
1 out of 52. So the answer here is going to be 17 minus 1, better known as out of 52, which reduces to 4 out of 13. Formula time.
So the only thing they had common was a 1.
Well, it only had one king of hearts.
Oh, you're talking about 1 out of the 4 faces.
Yeah, well, when you're looking at kings and you're looking at hearts, you have to go, well, is there any overlap between a king and a heart? There's a thing called the king of hearts. It's a single card, and it just gets counted as a king and a heart.
Oh, there's only 1 of them.
There's only one king of hearts.
Oh, okay.
Now, if I said, what's the probability of selecting a king or a red card? Well, how many red kings are there? 2, a diamond and a heart. So you'd have to get rid of 2, which is different. So, the formula that you need to know, the probability of A or B is equal to the probability of the first one plus the probability of the second one, minus the probability of their overlap. Each one of those probabilities that I've written up there, the P's, each one of them has to be an individual selection. You're only picking one card. You're not picking multiple cards. And is usually used for multiple, where you're picking one thing and then another. But in this case, it's one selection. It happens to be an A and a B at the same time. So this is what I consider the overlap. So you can also put in there the probability of the overlap subtracted away. What other fun things can I torture you on?
You only do this when you have an overlap.
Well, let's put it this way. What's the probability of being a king and a number card? 0. So then this probability would be 0, and all you're doing is adding the first two numbers. So I would highly suggest you use this formula all the time to keep thinking if they do have an overlap, you better put it here. If they don't have an overlap, 0 is perfectly fine.
How you gonna know?
You have to ask yourself, is there anything in common between this and that?
And they gonna always use cards, because I
No.
don't understand.
No, it could be tables like this.
Oh.
And what's funny is people usually get the cards right and screw up the table,
Yeah.
Oh.
which is really interesting. Never understood that. For example,
Cut 0. I can't read that number.
68%.
68. Oh, I see it now. Oh, you marked through something. And what?
Either. One or the other. I think that'll work out.
It's kind of accurate. And it's kind of true.
I'm making up numbers. No, it's not kind of true.
And either is.
So, when you come to this problem, there's two ways it's written. This here, when you see the word either, the word that comes to mind is or, because literally it's usually written either or. Either or. Both together at the same time must be the word and. So the first thing you want to find is the and the or in the problem. By the way, if it has an or, usually it has a and. And by itself is something totally different than this. But if and or are in the same type of problem, it's that formula up there. If and is by itself, it's multiple selections. Multiple selections. So you start off with the probability of math or biology is equal to the probability of, no numbers now, formula first. Probability of math, next, plus the probability of bio, minus the probability of math and biology. Okay. Underneath it, you put in the numbers that you know. Do I know math or biology? Yeah, what is it?
68. 70.
Or is 70%. So this becomes 70%. Math is 68%.
Hold on, what are you doing?
I'm plugging in numbers into the formula. Probability of math or biology is either or, which is 70%. The probability of math is 68%. The probability of biology is 73%. What?
I don't know.
What? Minus, do I know the probability of math and biology?
No.
So you call it x. So we need to solve for x. So what should I do first?
Okay, hold on.
Either
part.
What part?
The either part.
Either or is the or part of your problem. The only or part of your problem is here. So that percent has to go in this position. The and part is the one we're looking for. So that becomes our unknown. The other ones we just know. Probability of math, probability of biology. So how do I solve? What do I do first?
You add 68 plus 73%.
So 68 plus 73 is
141.
141 minus x
Yes.
percent, but I'll just leave it as x.
Subtract 141%
And you get,
from both sides.
yeah. Negative 71?
I can do it.
Is it negative 71?
Yes.
Yeah. So this would be negative 71% is equal to negative x. Therefore, x must equal
71%.
71%. So the probability of passing both is 71% of the time.
That's low.
That's pretty good.
That's pretty good.
Oh, you're not looking at it as a.
You're passing math and biology.
Oh, okay.
You're passing both
And
of
I'm
them.
taking math and biology, math and A and P too.
That's a biology.
And it's rough.
It can be. So that's not a hard problem as long as you are clear where the or goes and where the and goes.
Okay.
Mr. Cloran?
Yep.
Is it just weird that 71 is pretty close to being in the middle of 68 and 73?
Wonder if that'll always be the case? No, not always. It could be 5. You could have a 5 here. I would just have to change the number on the other side to be smaller. Or bigger. So yeah, it could be anything.
What time is class over?
Whenever I say it is.
Is it 11:20? When is it?
10 minutes.
This is the hard one.
Oh,
Oh,
got an asterisk by that too.
And I'm going to change gears in how I ask the problems. Multiple selections. I don't want to do it with cards. Cards gets a little tricky. Dice is kind of boring. So we're going to switch to
children.
no children. They're just like coins.
I wish you'd show us a problem.
Oh my God, children are like coins.
I can't get it.
It's a
right.
concept. It's a concept.
Okay.
Go with it.
Mr. K, we got 10 minutes.
I got 10 minutes to teach you this. This won't take too long. So what we're going to do is
in the back of. There's 16 marbles.
I could do that too.
Keep going, keep going.
I think it's the headless now.
Wow, that didn't come out. Rocks. I have a funny story, but I'm not going to say it. We don't have time. No, we don't have time.
No, we don't want to.
So,
How many?
probability of selecting
20 white rocks.
a red rock. How would you find the probability of selecting a red rock? What would you do first? Add together. 4 plus 12
16.
plus 20.
36.
So the bottom number is always going to be 36, unless we, remove some of these rocks. All right, and the number of red rocks?
It's 4.
4. My favorite thing is, I'll say something like, what's the probability of selecting a red rock out of this bag? And people will say, they'll think of, pulling that red rock out of the bag, and they'll say 1. Because in their hand there is 1 rock. But the idea is, how many of those rocks were red to begin with, which is the 4. So be really careful about it. You're not thinking about the one that's in your hand. You're thinking of how many different possible ways could you get it in your hand. So it would be 4 out of 36, better known as
1 9.
1 9.
1 9.
Is it 1 6?
Yeah. 1 9. So we could do this. What's the probability of selecting a red and then another red?
Wait.
So in other words, instead of just making one selection, now I'm making 2. Now there's 2 different ways to make this selection. I can pick the rock out, look at it, put it back in. That's called with replacement. So this is going to get split into 2 ideas. With replacement, the answer is going to be different than the other one, which is you pull the red rock out, you look at it, and you set it down off to the side. And you leave it outside of the bag. Then you reach your hand in again, and you select another one, and you're hoping to God it's a red rock, and you also set it down to the side. So outside the bag, you will literally have 2 red rocks. Where with replacement, you're just going to be looking at them individually, kind of like catch and release. All right, so this one is
4:30.
without
Oh.
replacement. There's other fancy words that go with it. This one is called dependent. This one is called independent. But I like with replacement and without replacement better. With replacement, the answer is this. What's the probability of selecting that first rock as red?
4 of 36.
4 out of 36. Now we're going to put it back in the bag. What's the probability of selecting another red rock?
4 of 36.
4 out of 36. What operation do I need to put in between them?
Addition. Wait. And
Or is addition.
Subtraction.
Mm-mm.
Division. Multiplication.
Addition.
Think about it. I mean, the probability of selecting the first one is the same as the probability of selecting the second one, but getting 2 in a row is not going to be bigger. It's going to be
Same.
smaller. So what the operation is multiplication. So if you see the word and without the word or, the main operation is multiplication. You see the word or, no matter where it is, it automatically turns into addition. Or is addition, and is multiplication.
you said if only if they don't have or.
Yeah, or automatically, you see or someplace in the sentence, it's the addition property. If and is the only word in the sentence, it's automatically with or without replacement multiplication. So it's 4 out of 36, you put the red rock back, it becomes 4 out of 36. How do you multiply fractions? Straight across. So the top is 4 times 4, the bottom is 36 times 36. I highly suggest you don't type that in your calculator. The best way to do it is literally 4 divided by 36 times 4 divided by 36. It equals. Don't you dare try to multiply them together. Because what will happen is you'll screw up over here. And on the calculator.
Could you say 1 9 times 1 9?
You could do 1 9 times 1 9. But in this case, I'm not going to ask you to say out of. I'm going to say what is the percent. Because the fraction 36 times 36 is a huge number, and I'm not going to be
1296.
4 out of 10,300,000. I don't care about that. What? Do 4 divided by 36 times 4 divided by 36 hit equals. What do you get?
I got one.
You
Okay.
cannot have 1, trust me.
I got zero.
Oh, I did.
0.0.
I did.
0 point,
Oh, you talk, oh, you know that.
Oh,
0 point,
hold on.
0, 1.
0, 1, 2, 3, 4, 5, 6, 7 now.
Seriously?
Yeah.
Yeah,
Oh,
it's
it's
eight.
cool.
Now, I'm going to change this to a percent. So what?
Times 100.
What? 4 divided by 36 times 4 divided by 36. If you try to do 4 times 4 divided by 36 times 36, you'll get the wrong answer.
I got
Okay.
1 out of 81.
Oh, you changed it to a fraction. So, is this 1 divided by 81?
Should be.
Check it, make sure.
1 divided, yeah, that's what I got.
So you're going to take this and times it by 100, and you're going to change it into, which would be
1.2%.
1.2% rounded to the nearest tenth of a percent. So when you do the decimal values, you'll at least need 4 of them to start with, but eventually you're going to round it down to 3. All right. So the probability of selecting a red rock and then another red rock with replacement is 1.2%. Without replacement works this way. Remember, you select the red rock, you set it down off to the side. So what's the probability of the first one being red? 4 out of 36. Times, now remember, that red rock is not in the bag anymore.
3 out of 36.
3 out of 35, because you removed a rock and it happened to be red. So this would be 3 out of 35. So 4 divided by 36 times 3 divided by 35 equals, is it going to be bigger or smaller than that?
It should be
Smaller. It'll be smaller. 0.01 something.
0.0095.
Oh, even worse. 0.00952.
952.
All right. You're going to multiply that by 100 and change it to a percent. It becomes
0.9.
0.95, right?
2, 3. 2.
But if I ask you to round it to the nearest tenth,
0.98.
point
0.
10.
point
1.
if you round it to the nearest tenth, this would be 0.1%. Because that 5.
Is approximately.
Well, on Moodle, if I say round to the nearest tenth, that's it. Now, some of them I have to go a little bit further because the probability is really tiny.
We want the one move over to.
Why wouldn't it be 1 whole percent?
Oh, you're right. You're
Yeah,
right.
so
You're
I'm
right.
like, what?
My brain was thinking something else. 1.0%. There we go. You're right. I love when I make mistakes and you all correct me.
What you